Having done the unit circle analysis for our understanding of simple harmonic motion, we are ready to graph the position, velocity, and acceleration with respect to time, and also consider what's called the phase angle. So here's our graphs, and we're going to represent one period here, t over 4, t over 2, 3t over 4, and t. So I'm going to map it through one period. And we discovered that the position x from the unit circle is a cosine of theta. Now, if you don't understand where that comes from, go back and re-listen to the last video. All right, so what's theta? Well, theta is simply omega t. All right, so that's good. We can graph this then. X is equal to a cosine omega t, which looks like this. So, no problem there. Now, how do we go to velocity? Well, you know that velocity is dx dt, and then that's going to be minus omega a sine omega t. So, derivative of cosine is minus sine. You bring the omega out front. Minus omega a sine omega t. And the maximum value of that speed is when sine of omega t is 1. So it's plus or minus omega a. So we're going to go ahead and put those limits in there. Omega a and minus omega a. And let's go ahead and graph it. There's negative omega a sine omega t. And you should be able to validate that the derivative of this position graph everywhere at every instantaneous point is the velocity. So up here is 0. Yep, 0. Maximum negative. Yep, there it is. 0 again. Slope of this here, 0. Maximum positive slope, etc. All right, now let's do it for acceleration. Again, it's the derivative of the velocity. So conceptually, we should be able to map it on here, no problem. It's going to be 0 here, maximum negative, all right? But what's the equation? Well, it's minus omega squared a cosine omega t. Just taking the derivative of this, bringing omega out again. There it is, squared. So the maximums are plus or minus omega squared a. So let's go ahead and put those limits in on the graph and plot it. There's the plot. And so this set of plots is all consistent with each other. And that expresses the various physical parameters with respect to time for SHM. A few comments are in order pertaining to something that we call the phase angle. And the phase angle really relates to the idea of the object in SHM starting in a non-zero, or not a simple, an arbitrary, say, starting location, where it's actually gone through a certain phase angle phi. Now this could correspond to a process where you're leading or lagging some other process that's cyclical in nature. Happens a lot in electrical circuits and can happen mechanically as well. So let's just get an idea how we handle this. So when t is equal to 0, x is equal to a cosine of phi. Right? So later on, we're at a new location. We've gone through some angle theta now. So here's theta. And phi is our initial starting point, denotes our initial starting position. So the object would be right there. Later on, it's right here. So then x is equal to a cosine of omega t plus phi. So you're combining those two angles, essentially, and coming up with our location x. Now, phi is called the phase angle, as already mentioned. Let's consider some initial conditions. If phi is equal to 0, then this thing reduces to x0 is equal to a. So if this is 0, then this is just 1, right? And actually, it makes sense, because if phi is equal to 0, this object is sitting right there, and x0, the initial position, is here at the amplitude a. Now, if it's pi, it's on the other side, and it's minus a. The velocity and acceleration equations become as follows. Velocity is, just from taking the derivative of the position, omega minus omega a sine of omega t plus phi, and acceleration minus omega squared a cosine of omega t plus phi. Now, if x is x0 and v is equal to v0 at t is equal to 0, which is logical, right? At time t is equal to 0, the position and velocities are their initial values. Time t is equal to 0. Then we have x0 is equal to a cosine of phi. The omega t is gone, so it's just a cosine of phi. Likewise, v0 is minus omega a sine of phi. Again, this is 0, so it's minus omega a sine of phi. Let's combine these together. We're going to divide these actually as follows. v0 over x0 gives us minus omega a sine of phi over a cosine of phi, which is minus omega tangent of phi. So we can solve for tangent of phi. Yay! Minus v0 over omega x0. And so this is a relationship between the tangent of theta, the initial velocity, the initial position, and the angular velocity, or angular frequency, whichever one you want to think of it as. This is not extremely important to worry about the details of this if you didn't understand it too well, but it is an idea that comes up in AP Physics. So there it is, and hopefully shed a little light on it.